March 31st, 2026, 2:17 UTC. NASA's Deep Space Network Operations Center at the Jet Propulsion Laboratory in Pasadena, California, was running as usual. A mission controller, working the overnight communications shift, sat at the console, preparing to receive a routine signal from Voyager 1. For 47 years, this procedure had been repeated almost daily, aligning the 230-foot dish at Goldstone against a tiny point of sky in a distant constellation, waiting for a signal weaker than a refrigerator light bulb to arrive from 24 billion kilometers away. The signal would take 22 hours and 35 minutes to travel that distance. There was nothing unusual expected, nothing to break the rhythm of decades of steady telemetry. The controller opened the data packet and began reviewing the plasma wave science return. Then he pulled up the magnetic field data from the MAG instrument. His chair rolled back slightly as he read the numbers again. Something was off. The readings didn't match the expected properties of the interstellar medium the very space Voyager 1 had been traveling through since 2012. The numbers didn't fit any region of space predicted by decades of physics models. This wasn't a minor anomaly. This was entirely unexpected. He didn't cue it through the standard anomaly channels. Instead, he called the Voyager project scientists directly, bypassing the usual hierarchy. By 4 UTC, 3 additional scientists had remotely accessed the same data from home. By 6:30 UTC, the readings had been cross-referenced with Voyager 2, positioned 320 degrees away, measuring the same interstellar medium from a completely different angle. The anomaly didn't resolve, it grew. This single overnight packet forced the Voyager team to confront a profound question: what exactly is the edge of the solar system? Voyager 1's historic 2012 crossing had been carefully documented, but now, 47 years of compiled data were challenging the very definition of that boundary. Every measurement revealed inconsistencies with the models physicists had relied on for decades. And the evidence wasn't subtle. It demanded a complete reassessment of the heliosphere's structure and the interstellar medium beyond it. To understand why, we need to revisit the theoretical foundation. In 1958, University of Chicago physicist Eugene Parker predicted the solar wind, a continuous outflow of charged particles from the sun's corona. This wind carries the sun's magnetic field outward, losing roughly 1 million tons of solar material every second. Traveling at speeds between 400 and 800 kilometers per second, these protons, electrons, and alpha particles form a vast bubble of influence around the sunday. Beyond this, the interstellar medium contains roughly 0.1 atoms per cubic centimeter, a near vacuum by earthly standards, but enough to exert measurable pressure across cosmic distances. Where the outward solar wind pressure meets the inward interstellar pressure, a boundary forms, the heliopause. This is theoretically the edge of the sun's direct influence. Before reaching the heliopause, the solar wind must pass through the termination shock, a region where the supersonic solar wind slows to subsonic speeds. The kinetic energy converts to heat, forming a transition zone analogous to a sonic boom. Beyond that, the heliosheath should contain smoothly flowing plasma, slowed and redirected around the heliopause like water flowing around a rock. By the 1980s and 1990s, models predicted a roughly spherical heliosphere, with the termination shock at 7590 astronomical units, the heliosheath 1020 AU thick, and the heliopause at 9100 AU. This was the picture that decades of physics seemed to confirm, but Voyager's real measurements would prove it far more complex. Voyager 1 crossed the termination shock on December 16, 2004, at 94 AU 4 AU beyond the predicted range. Voyager 2 crossed at 84 AU in 2007, nearly 10 AU closer than Voyager 1, traveling just 47 degrees south of its counterpart. These differences weren't small, they shattered the assumption of a spherical, symmetric boundary. The heliosphere was asymmetric, stretched and compressed by the interstellar headwind as the solar system moved through the galaxy. The solar wind slowed differently than expected. The temperature increase at the termination shock was far lower than predicted, and the missing energy remained unaccounted for. Inside the heliosheath, the models failed again. Rather than smooth plasma flow, the spacecraft detected magnetic bubbles, hundreds of them, each larger than the distance from Earth to the Sunday. These bubbles deflected cosmic rays, created filtering structures, and redefined how we understand the Sun's magnetic influence at the edge of the solar system. And the moment both spacecraft crossed the heliopause, more surprises emerged. Magnetic field direction remained consistent across the boundary. Solar wind ions disappeared. Galactic cosmic rays flooded in. Yet the interstellar magnetic field aligned with the Sun's field in ways no model predicted. The hydrogen wall was thicker than expected. Interstellar plasma oscillated in response to solar activity. The boundary wasn't a wall, it was a permeable, dynamic membrane, and the Sun's influence extended far beyond the predicted limits. Voyager 1 now operates on just 249 watts, its instruments shutting down slowly, its final signals fading toward cosmic silence. But every last packet carries evidence that the solar system's edge is far more intricate than imagined, a living structure linking the Sun to the galaxy in ways that challenge our deepest models of physics. The question now is not whether humanity will eventually cross this boundary. It's what the heliosphere's true structure tells us about the Sun, the interstellar medium, and our place in the cosmos. And the next transmission will take us further than any spacecraft has ever gone, uncovering discoveries that will change everything we thought we knew about the edge of our solar system. As Voyager 1 pushed beyond the termination shock and into the heliosheath, the spacecraft revealed a reality that no model had predicted. The heliosheath was not a calm, uniform flow of slowed solar wind. Instead, it was a turbulent foam filled with discrete magnetic bubbles, each roughly 100 million miles across, larger than the distance from the Earth to the Sunday. These weren't occasional anomalies. They were the dominant structural feature of the heliosheath. Each bubble was a product of magnetic field lines disconnecting and reconnecting, a process theorists had considered minor, almost negligible. Voyager data proved otherwise. This structure fundamentally changed how we understood cosmic ray transport, as the bubbles did not merely slow incoming particles, they trapped, redirected, and filtered them along bubble boundaries. The geometry of the bubbles controlled the movement of high-energy particles, creating a system far more complex than a simple pressure gradient could explain. The Voyager mission has now accumulated 47 years of measurements, and each confirmed discovery adds to the picture of a heliosphere, nothing like the one physicists had predicted. The termination shock was not a stationary boundary. It was dynamic, responsive to solar activity. Voyager 1 recorded the shock moving inward and outward over time, retreating under coronal mass ejections and advancing when solar wind pressure increased. Voyager 2 recorded similar oscillations. These shifts proved that the outer boundary of the solar system is not a fixed edge. It's a flexible, living structure, sensitive to the Sun's output and to the interstellar environment. The asymmetry revealed by Voyager 2 was equally shocking. Its termination shock crossing occurred 10 astronomical units closer to the Sun than Voyager 1's, despite being separated by only 47 degrees of angular distance. This finding demolished the idea of a spherical heliosphere. Instead, the heliosphere was compressed on one side by the galactic headwind and stretched on the opposite side, forming an unexpected tail structure. The standard models, which treated the solar wind as uniformly outward and the heliosphere as roughly spherical, could not accommodate these measurements. The solar system, it seemed, had a shape molded by the surrounding galaxy itself. Then came the energy problem at the termination shock. The kinetic energy of decelerating plasma, according to classical shock physics, should convert almost entirely into heat. But Voyager 2 showed that this wasn't happening. The plasma slowed dramatically, yet the temperature increase was far lower than predicted. Where the energy went remains an open question, a missing piece in the energy budget that continues to challenge heliophysics to this day. Scientists have been forced to reconsider the dynamics of plasma flow and magnetic interactions at the solar system's boundary. Crossing the heliopause brought even greater surprises. Voyager 1 did so in August 2012 at 121.6 AU. Voyager 2 inches November 2018 at 119 AU. Models predicted a clear rotation of the magnetic field direction, signaling the transition from solar to interstellar influence. Instead, the field direction remained essentially unchanged. Solar wind ions vanished, galactic cosmic rays surged in, yet the magnetic orientation held. This alignment between the Sun's magnetic field and the local interstellar field was completely unanticipated. The interstellar medium, previously thought to be independent and unaffected by the Sun, was clearly responding in a coordinated way. Beyond the heliopause, both spacecraft observed the hydrogen wall, compressed neutral hydrogen atoms accumulating at the boundary between the solar wind and interstellar medium. Its thickness was far greater than predicted, revealing a structural complexity that standard pressure balance models had never accounted for. Additionally, interstellar plasma displayed oscillations triggered by solar events. Even in the depths of interstellar space, the Sun's influence persisted, ringing the medium like a distant bell. The boundary was not a simple wall, but a permeable membrane, extending the Sun's electromagnetic reach far beyond any prior estimate. All of this points to a conclusion that challenges the very models that guided decades of research. The heliosphere is not a bubble. It's an asymmetric, foam-filled, magnetically continuous structure dynamically connected to both the Sun and the galaxy. The missing energy at the termination shock, the unrotated magnetic field at the heliopause, the hydrogen wall thickness, the oscillating interstellar plasma, all these anomalies suggest that the solar system is far more active and interconnected with its galactic environment than scientists had imagined. Voyager 1 now drifts 24 billion kilometers from the Sun, transmitting a 2-3 watt signal, a whisper from a distant past, carrying measurements that continue to rewrite our understanding of the cosmos. Its data reveal not just what lies at the edge of the solar system, but how our star interacts with the galaxy at large, and how the boundaries we once imagined are actually complex, dynamic structures that defy classical physics. The next part will take us deeper, analyzing the implications of these discoveries on cosmic ray behavior, the Sun's magnetic influence, and why the very concept of a heliosphere as a simple, protective bubble must be rethought. As Voyager 1 and Voyager 2 pierced the heliopause, they entered a region once thought to be empty and simple interstellar space, but the reality was far more intricate. The magnetic foam of the heliosheath didn't just disappear at the boundary, it transitioned, merging with the interstellar magnetic field in ways that no model had anticipated. This revealed an unexpected continuity. The Sun's magnetic history imprinted itself on the local galactic environment. What we assumed to be independent fields, solar and interstellar, were actually linked, aligned along a direction dictated by the Sun's own past activity. The implications are profound. It suggests the solar system is not a passive bubble floating through space. It actively interacts with and shapes its surroundings, even hundreds of billions of kilometers away. The cosmic ray patterns Voyager detected confirmed this connection. Previously, models assumed cosmic rays traveled into the heliosphere according to simple gradients of pressure and density, slowing as they encountered the solar wind. Yet Voyager data showed that the foam bubbles acted as a complex filtering network. Charged particles weren't merely slowed, they were trapped, redirected, and guided along the bubble boundaries. The arrangement of these bubbles determined how many cosmic rays reached the inner solar system. Our understanding of space weather, the radiation environment around Earth, and even the protection afforded by the sun's magnetic field now had to be reconsidered. The heliosphere was functioning as a sophisticated particle sieve, far more organized than any theory predicted. Even the hydrogen wall, once considered a minor boundary effect, revealed unexpected depth. Both Voyagers detected a significantly thicker accumulation of neutral hydrogen atoms than anticipated, indicating that the interaction region between the solar wind and interstellar medium was not a single boundary, but a multi-layered structure with complex dynamics. This structure likely influences not only the penetration of galactic particles, but also the distribution of interstellar matter and energy as it flows past the solar system. What was previously treated as a simple pressure equilibrium became a highly structured transition zone. Voyager's observations also upended assumptions about the behavior of the interstellar medium itself. The plasma beyond the heliopause was not electrically quiet, as models had predicted. It oscillated in response to solar activity, coronal mass ejections, and pressure pulses that traveled across light hours of distance. The sun, it seemed, could reach out and ring the local interstellar medium like a cosmic bell. This continuity challenges the notion that interstellar space is detached from solar influence. Instead, it is responsive and connected, demonstrating a level of complexity that physicists had not anticipated. Every new dataset added to the picture, the termination shock oscillations, the asymmetric heliosphere, the foam bubbles, the unrotated magnetic field at the heliopause, the hydrogen wall thickness, and interstellar plasma responsiveness. Taken together, they formed a coherent narrative. The solar system's outer boundary is not static, not spherical, not independent. It is a dynamic, permeable structure, continuously influenced by the sun, while simultaneously interacting with the surrounding galaxy. Classical models of the heliosphere as a protective bubble were no longer adequate. They had to be replaced with a more nuanced understanding of a membrane-like structure where magnetic, plasma, and cosmic phenomena intersect in ways that blur the line between solar and interstellar space. From a theoretical standpoint, this challenges decades of physics. Hydrodynamic and magnetohydrodynamic equations, foundational to modeling the heliosphere, could not fully reproduce the observed features. The missing energy at the termination shock, the persistence of magnetic field alignment across the heliopause, and the structural complexity of the foam bubbles all point to mechanisms not accounted for in standard models. Researchers now face the task of reconciling observed reality with theoretical expectations, a process that could redefine the boundaries of space physics. Voyager's journey also carries a philosophical weight. The spacecraft is powered by a radioisotope thermoelectric generator producing just 23 watts. Its computers are weaker than a modern wristwatch, yet it continues to provide measurements that challenge humanity's understanding of the universe. Its golden record, a message in a bottle to the stars, will outlast the civilization that created it, traveling for tens of thousands of years through the galaxy. But beyond the message it carries, Voyager delivers something far more important: raw data that forces us to rethink our place in the cosmos. By 2026, the data window is closing. Instruments are gradually shutting down, and the radioisotope power source declines steadily. Each remaining packet from Voyager 1 and 2 becomes increasingly valuable. They are the last living witnesses to the outer structure of our solar system, capturing details that decades of simulation and theory could not anticipate. Every anomaly recorded is a clue, every deviation from the model, a revelation about the true complexity of the sun's interaction with its galactic environment. The next part will explore the 9 key discoveries of Voyager, the unexpected energy flows, and the structural surprises at the boundary that collectively force scientists to rewrite the heliosphere from the ground up. We'll see why these measurements are not minor anomalies, but a systematic overhaul of decades of theoretical predictions. Now, let's dive into the 9 Voyager discoveries that fundamentally reshaped our understanding of the solar system's edge. Each of these findings wasn't just a minor correction to existing models, they were structural revelations that no simulation had predicted, forcing a complete rethink of the heliosphere. First, the termination shock was not a fixed boundary. As Voyager 1 approached it in 2004, it crossed at 94 AU beyond the upper limit predicted by the models, but the shock didn't behave like a rigid wall. It fluctuated, breathing in response to solar activity. Coronal mass ejections pushed it outward, then as solar wind pressure decreased, it contracted inward. Voyager 2 observed similar behavior in 2007, crossing the termination shock 10 AU closer to the Sun than Voyager 1, despite only a 4-7 degree separation in their trajectories. This confirmed the boundary's asymmetry and dynamic nature, a reality that spherical, static models simply could not capture. Second, the missing energy at the termination shock presented a profound puzzle. The kinetic energy of the solar wind, as it slowed from supersonic to subsonic, should have converted almost entirely into thermal energy. Voyager 2's plasma instruments revealed the temperature increase was far below expectation, leaving a significant portion of energy unaccounted for. Where it went remains one of the enduring questions of heliophysics. Third, inside the heliosheath, the spacecraft detected discrete magnetic bubbles, forming a foam structure across the plasma. These bubbles, each roughly 100 million miles wide, were created by repeated magnetic reconnection events. Far from being occasional irregularities, they dominated the structure of the heliosheath, filtering cosmic rays and altering the expected energy and particle transport into the inner solar system. Fourth, the foam was more than just a local oddity. It connected directly with the interstellar medium, suggesting the Sun's influence extends well beyond what classical models predicted. Fifth, the heliosphere proved to be asymmetric. Pressured by the interstellar headwind, as the solar system moves through the galaxy at 220 kilometers per second, the termination shock and heliosheath were compressed on one side and stretched into a long tail on the other. This contradicted decades of models that assumed a roughly spherical shape. Sixth, the hydrogen wall detected at the heliopause was far thicker than expected. Neutral hydrogen atoms accumulated, forming a dense, structured region that modifies how interstellar material enters the heliosphere. Its existence demonstrates that the Sun's influence continues to interact with the galactic environment in a non-trivial way. Seventh, the interstellar plasma itself is not quiescent. Voyager detected oscillations and electron density fluctuations triggered by solar activity, indicating that the Sun can ring the surrounding medium like a bell, even across distances measured in light hours. Eighth, the magnetic field direction across the helopause remained remarkably unchanged. While particle populations shifted dramatically and solar wind ions disappeared as galactic cosmic rays poured in, the alignment of the Sun's magnetic field with the local interstellar field persisted. This alignment, completely unpredicted by models, implies that the heliosphere is not a passive structure, but a dynamic system maintaining an active relationship with its environment. Finally, the 9th discovery is perhaps the most profound. The heliopause is permeable. Solar influence does not stop at the boundary. Electromagnetic and plasma effects continue well into interstellar space. Combined with all other anomalies, the asymmetric shock, missing energy, foam structure, hydrogen wall, responsive interstellar plasma, and magnetic alignment, the Voyagers painted a picture of a complex, active interface between the Sun and the galaxy. These 9 discoveries collectively demolished decades of theoretical assumptions, revealing the heliosphere not as a bubble, but as a living, dynamic membrane. What's remarkable is that none of these discoveries required exotic assumptions or alien intervention. They emerged naturally from the data, yet they demand a reconsideration of what it means to model a star's interaction with its environment. Humanity now understands the heliosphere as a structure that is dynamic, asymmetric, foam-filled, and magnetically continuous with the galaxy, challenging our most basic assumptions about the solar system's boundary. Voyager has given us a first-hand look at a transition zone where the Sun and galaxy interact with surprising complexity, demonstrating a relationship that is far from passive and far from uniform. Next, we'll explore the implications of these discoveries in terms of energy transfer, cosmic ray propagation, and the long-term dynamics of the solar system as it journeys through the galaxy. We'll see how these findings reshape the concept of what it means to reach the edge of our solar system, and why the boundary isn't a wall, but a dynamic, structured interface that continues to surprise and challenge our understanding. Now, let's focus on the energy dynamics and cosmic interactions that make the heliosphere far more complex than the early models predicted. One of the most striking findings from Voyager's long-term data is the apparent missing energy at the termination shock. The solar wind, moving at hundreds of kilometers per second, should convert its kinetic energy into thermal energy as it slows and interacts with the interstellar medium. Voyager 2 showed us that this energy simply wasn't appearing in the expected forms. The plasma didn't heat up as much as physics predicted. So where did the energy go? The answer isn't fully known, but the implications are profound. It hints that the solar wind's energy is being transferred into processes or structures that we are only beginning to understand, such as the formation of the magnetic bubbles in the heliosheath, turbulence, or electromagnetic interactions that extend far beyond the visible boundary. The magnetic bubble foam itself is a major clue. Imagine hundreds of enormous magnetic islands, each roughly 100 million miles across, floating within the heliosheath. These structures aren't just passive, they interact with charged particles in highly organized ways. Cosmic rays entering the solar system aren't simply slowed or deflected by a smooth plasma gradient. They are channeled, trapped, and guided along the edges of these magnetic bubbles. This creates a filtering effect, controlling the type and intensity of cosmic radiation reaching the inner solar system. Such a mechanism was completely unpredicted by any prior models. Instead of a simple pressure balance, the heliosphere behaves like a structured magnetic labyrinth, capable of organizing energy and particles in ways that are still being studied today. Another astonishing feature is the asymmetric nature of the heliosphere. Voyager 1 and Voyager 2 crossed the termination shock at very different distances, confirming that the solar wind's interface with interstellar space isn't a symmetrical bubble. The solar system plows through the galaxy at 220 kilometers per second, creating a headwind of interstellar material that compresses one side of the heliosphere while stretching the opposite side into a long tail. This configuration wasn't just a minor deviation from theory, it is a large-scale structural feature that completely reshapes our understanding of the solar system's outer boundary. The tail and head regions are functionally different, with the head facing a higher interstellar pressure and turbulence, while the tail allows solar material to extend farther, creating an elongated, dynamic interface.